Learning Unit 3, Defects in Crystals. Defects in crystals may be categorized according to their dimension. We'll deal with point defects, which are zero-dimensional, line defects, which are one-dimensional, and area defects, which are two-dimensional. Point defects encompass the following types. We can have a vacancy. Notice that the vacancy is a missing atom in a crystal, and it causes a deformation in the crystal. This deformation is called a strain field. The strain field is larger in extent than the actual size of the missing atom, and this indicates that the actual particle or defect, the size of the defect can be much smaller than the effect it has on the overall crystal, and this is important for considering things such as strengthening mechanisms. In B, we see an interstitial defect. This is where an atom is placed between the spaces in the atoms within the crystal. In C, we see a small substitutional defect. Here, one of the atoms in the crystal has been substituted with a smaller atom, and this has resulted in a strain field. An alternative method to create a strain field is to put a larger atom as a substitutional atom, and that's shown in D. In E, we have a Frenkel defect. A Frenkel defect is a vacancy which is associated with an interstitial defect. So basically, an atom has been shifted from its regular position into an interstitial position. In the Schottky defect, we have missing ions in an ionic crystal in such a way that the overall crystal still remains neutral. So we have an equal quantity of positive ions missing as negative ions. As discussed, this is the vacancy defect that we talked about, the interstitial defect, small interstitial, large interstitial, the Frenkel defect, and the Schottky. Here we have more clearly put here a vacancy pair of oppositely charged ions. So what causes point defects? Temperature, mechanical processing such as deformation, impurities, or doping, which is deliberate introduction of impurities, or nuclear radiation of the material. At any temperature, there will be an equilibrium concentration of vacancies, which can be determined using the following equation. NV is the vacancy concentration, N is the number density of atoms in the materials, QV is the activation energy required to create 1 mole of vacancies, R is the gas constant, and T is the temperature in Kelvin. The units may change, and let's have a look at this problem here. Calculate the number of vacancies per cubic meter in iron at 850 degrees centigrade. The energy for vacancy formation is 1.08 eV per atom. Furthermore, the density and atomic weight of iron are 7.65 grams per centimeter cubed at 850 degrees centigrade and 55.85 grams per mole respectively. So the equation that we studied in the last slide is as follows. In this case, we see that the energy for the vacancy formation is given in electron volts per atom. In such a case, it's better to use this equation here. I'll just call this Q2. Okay, so Q2 is per atom. In such case, instead of using the ideal gas constant in the denominator here, we're going to use Boltzmann's constant. And we see we're using units of EV, electron volts. So what we want to do here is use Boltzmann's constant in EV units, and we'll get to that. First thing we should do, of course, is to convert the temperature to Kelvin. Which is 1123. Next we want to calculate N, the number of atoms per unit volume. To calculate that, let's look at the density. Density is mass over volume. This is equal to the number of atoms per unit volume multiplied by the mass of each atom. So we can see that this quantity here is N, the quantity we're looking for. The mass of each atom is the relative atomic mass of iron divided by Avogadro's constant. And the density is mass over volume, which is given in 7.65 grams per centimeter cubed. We're required to calculate the number of vacancies per cubic meter, so we do need to convert this. So 7.65 grams per centimeter cubed. We want to multiply this by the number of centimeters in a meter cubed, so, or centimeter cubed in a meter cubed, which is 10 to the 6 centimeter cubed per meter cubed. And then this is fine because this quantity is in grams and this quantity is in grams, so they will cancel. But we do need to convert the centimeter cube from grams per centimeter cubed to grams per meter cubed. So we've got this equation and we can solve for N. Divided by the atomic mass of iron, which is 7.65. Oh no, it's not. It's 55.85. Excuse me. And we can calculate this out. So I've calculated that to be 8.25 times 10 to the 28 atoms per meter cubed. Now in this equation here, we've found N, we've got T, we've got Q sub 2, which is the energy for vacancy formation, here given in electron volts per atom. So what we want is K, the Boltzmann constant, in electron volts. So doing a quick Google search, we see that the Boltzmann constant in electron volts is 8.62 times 10 to the minus 5. Now we can calculate the concentration of vacancies. So we have N equals 8.25 times 10 to the 28 atoms per meter cubed. We're going to multiply that by E. So I can put, actually I'll just put E. E to the minus Q. Q is 1.08. Electron volts per atom. And this is the Boltzmann constant here. And that's 8.62 times 10 to the minus 5. And this quantity is in electron volts. So you see that actually electron volts per Kelvin. So you see the electron volts on at the top here cancel one on the bottom, and then we're going to multiply this quantity here by the temperature in Kelvin, which is 1123, and calculate that out. After calculating that out, I got 1.18 times 10 to the 24 vacancies per meter cubed. And this is the solution for NV. So the key to these kinds of problems is to be careful with the units in regarding the units of the given quantities and the units of the required quantities, and just be careful that you use, when you find the constants, that they have the appropriate units for the input numbers. Okay, so what we calculated there was the equilibrium vacancy concentration at a certain temperature, but often we find that the actual vacancy concentration is different from that equilibrium value, and the reason for that could be the material could have been rapidly quenched from high temperatures, so it wasn't given the chance to achieve an equilibrium. The composition of compounds, of intermetallic compounds in particular, could have been created from a melt that deviates from what's called the stoichiometry, which is the ratio in which the elements occur in the compound. If the material is bombarded with high energy nuclear particles, we can increase the number of vacancies. Cold working. So cold working is when we deform the material below a certain temperature, which is specific to the material. And in some metals, the oxidation is accompanied by the formation of vacancies. Vacancies can be important for the operation of certain types of technical ceramics. So for instance, here we have a zirconium dioxide ceramic here, which is created so that it has vacancies within there to allow diffusion of oxygen from the environment into the device. And the way that this works is there's electrical signal that is created by the diffusion of oxygen into the device, and you can measure oxygen concentration. And these are found in most of the cars in California have an oxygen sensor in there as part of the emission control system. With impurity defects, it's difficult to purify metals over 99.9999. Hopefully I said enough nines there, percent. If we deliberately introduce impurities, that's called alloying or doping. So these impurities can result in a solid solution, which is in the end you have a single phase material, which is simply a mixture of the elements that you've combined, or the elements that we've put in react to form a second phase. And here we discussed before about the difference between a substitutional impurity atom and an interstitial impurity atom. And you can see that the likelihood of an impurity to be located at a substitutional site or an interstitial site will depend on its size. When combining different materials to result in an alloy, these rules have been determined to be useful for determining whether we get a solid solution. And these are known as the Hume-Rothery rules. If the solute atom it is within plus or minus 15% of the size of the host atoms, then the solid solution is probable. If not, then we'll probably get a second phase. The solid solution is likely if the solvent and the host have the same crystal structure. Okay. 3. If the electronegativities of the solute and the host are very different, then the second phase or intermetallic is likely. Valency. So the crystal structure is sensitive to the reduction in valency of the constituent atoms. Therefore, a solute atom of a high valency will be likely to have a high solubility in a host of lower valency atoms. So we can apply that to making some predictions. Here we have some elements, their atomic radii, their crystal structure, the electronegativity, and their valence. In this question, the atomic radius, crystal structure, electronegativity, and the most common valence are tabulated in the following table for several elements. And those that are non-metals, only atomic radii are indicated. Which of these elements would you expect to form the following with copper? A substitutional solid solution having complete solubility. Okay, so let's have a look. If we want complete solubility, then we want to meet all of these Hume-Rothery rules. So first, let's have a look at the atomic size. So the atomic radius of copper is 0.1278. So I'm going to calculate plus or minus 15% of that. So calculate plus or minus 15, and we get radii within 0.109 and 0.145 nanometers, plus or minus 15 of the radius of the copper atom. So let's have a look which ones meet that criteria, which is the first of the Hume-Rothery rules. So carbon is too small, hydrogen is too small for that, so is oxygen. Silver is good, just about. So I'll just put an A there. Aluminum, in range. Cobalt, in range. Chromium, is in range, yes. Iron in range. Nickel is in the range. Palladium, yes. We've got platinum, yes, and zinc. So okay, on the basis of rule 1, we haven't ruled out any of the metals. The non-metals will not form a substitutional solid solution. So now let's have a look at rule 2. Rule 2 is solid solution likely if the solvent and the host have the same crystal structure. Okay, so let's have a look at same crystal structure. Copper is FCC, so silver, that's good. Aluminum's good. Cobalt is HCP, so we're going to remove this one from my list. These are all BTC, so we'll remove these. Nickel is FCC, so I'll leave that one. And then the last one, zinc, is HCP. So what we're left with all the FCC crystal structure metals. All of them meet the first criteria, and now we've limited it down to the second one. If the electronegativity of the solute and the host are very different, then the second phase of intermetallic is likely. So here, let's have a look at the copper is 1.9, silver is the same, aluminum is 0.4 difference. Although there's no exact kind of cutoff given, I would say that's quite a small difference. Well, that's quite a small difference, unlikely to result in a compound. And we've got nickel, palladium, and platinum. Well, they're all within similar ranges and unlikely to definitely give us some kind of compound just on that one criteria. So that seems pretty good. Okay, crystal structures are sensitive. So if the valency of the solute is higher than that of the solvent, we've got a better chance. So valence, the copper has a valence of +2, so it should dissolve readily in silver, yes. So that's a strong candidate here. This is higher, so probably not on the valence. That one has been disqualified, and these are all the same, +2, +2, +2. So from this analysis, we can say that all of them, apart from aluminum, are, according to the rules, have a high potential for forming unlimited solid solutions. So whether that's actually realized in practice is not completely determined by the 4 rules, but serves as a guide. Okay, let's have a look at the next one. A substitutional solid solution of incomplete solubility. So we would expect from, well, let's just, we can list, we can put well, I'll put A for the solutions to part A, and I'll remove this one here. Okay, we're not sure because it has a higher valence. Now for B of incomplete solubility, we can suggest B. We can suggest cobalt and chromium and zinc. These have different crystal structures. An interstitial solid solution. So these over here are candidates for that. Now what we can do, we can go back and look at the sizes of interstitial sites relative to the radius of the atoms and see if these nonmetals are likely to fit those positions. Here I've reproduced a table that gives us the radius ratio for different interstitial sites that were shown in the previous lecture, in the previous chapter. This is an FCC lattice. We know that copper is FCC, and we have octahedral and tetrahedral sites. Here I've listed the atomic radius of copper, carbon, hydrogen, and oxygen. And then I've expressed each one as a ratio of the radius of the copper atom. So we see that carbon here has a radius ratio of 0.6. Let's call it 0.6. So it will not fit in these two positions. It won't fit in the tetrahedral site. It could fit in the octahedral site. So let's put copper as a candidate. Carbon as a candidate for an octahedral interstitial site. Actually, this one's correct. I was looking at hydrogen. So look at hydrogen now. This is 0.36. You see, it's a little bit too small to fit in the octahedral site, or octahedral site. The tetrahedral site would be a good candidate for the hydrogen. It could fit. Oxygen has a radius ratio of, let's call it 0.5, and so that looks like it will fit in the octahedral site. Okay, so now we've established which of these elements can fit in interstitial sites. And then it says an interstitial solid solution. Oh yeah, that's part C. Yes. So sorry, that's part C. That's what we were just doing. There we go. When we're alloying two elements together, or any number of elements together, one common way to express the composition is to use weight. Now what this really means is mass percent. And the way we calculate mass percent is we take the mass of one element in the material and divide it by the sum of all the mass of all the components. So, for example, if we mixed 90 grams of copper with 10 grams of gold, this gives us a 10 weight percent. Oh, did I say gold? I wrote the symbol for silver. So this is 10 weight percent silver, copper silver alloy. So we've looked at point defects. Now we're going to move on and look at line defects. Here we're shown an example of a dislocation. So imagine we have a perfect crystal. If we were to imagine a cut like so, and then we displaced one part of the cut with respect to the other and rejoined it, we would get a dislocation. The dislocation is characterized by the line of the dislocation, and I'll show you some more detailed pictures of that visually. This is the step here is due to a screw dislocation on the surface of a crystal. So let's look at the two different types of line dislocation. So this is an edge dislocation. Okay, this type is an edge dislocation. And you can, if we look at this crystal, you see what's happened to it is it's as though we had inserted an extra set of planes, an extra plane, in the region hatched red. The bottom edge of that extra plane is highlighted and it's being given this symbol zeta. Oh, I think that's a zeta. So let's just let's call it a zeta for now. So and we've been given a direction here. So how do we measure some characteristics of this? One characteristic of this is obviously the line of the edge dislocation, which is shown here, and there's something called a Burger's vector, named after the inventor of this system of notation. There's different conventions, and we're going to use the right hand start to finish convention, sometimes referred to as RHSF. So to do that, what we do is we, having established our direction of our line dislocation, I'm using my right hand to denote a counterclockwise path in the crystal around the dislocation. What the Burger's vectors does is it gives an idea of the distortion introduced by the dislocation. So we establish a start here at one of the lattice points here, and then we're going to traverse a path that should be closed on a perfect crystal. On a perfect crystal, if we step 1, 2, 3, 4 steps here towards the left, and then go down 1, 2, 3, and now we step 1, 2, 3, 4 towards the right, and then we go up 3, 1, 2, 3, we should have, if the crystal was undistorted, we should have ended up at our start position, but we did not. The difference between the start and the finish gives us an idea of the distortion created by this dislocation. This vector here, called the Burger's vector, points from the start port location to the finish location. So that's how we determine what's called a Burger's vector. We can tell this is an edge dislocation because the line of the dislocation here, which is the bottom of the edge of this inserted plane, is perpendicular to the Burger's vector. Let's try again, just to illustrate the point. So what we have here, we have a dislocation. We have an edge dislocation here. Let's have the line of the dislocation come out of the page. So we want to create a counterclockwise loop. That would be using the right hand to give us that direction. Then we want to pick a loop that goes around the dislocation, and let's pick a start point. Let's say we start here, and I'm going to make a path, which is a rectangular path. Okay, so which should, in a perfect crystal, should come back to the start position. So let's make 1, 2, 3, 4 steps here. Let's go down 1, 2, 3, 4 to completely encompass this dislocation. As I went across to the left by 4 steps, I want to go towards the right by 4 steps. 2, 3, 4. As I came down 4 steps, I want to go back up 4 steps. 1, 2, 3, 4. 1, 2, 3, 4. Now what I found is that the start and the finish were not the same point. So my Burger's vector goes from the start to the finish. That's my Burger's vector for this dislocation. Another type of line dislocation is the screw dislocation. Let's apply the same technique to determine the Burger's vector for the screw dislocation. We're starting at this point over here. We're going down 1, 2, 3, 4. We're going across 1, 2, 3, 4. We're going to go up again 4 steps, 1, 2, 3, 4, and we're going to go towards the left 4 steps, 1, 2, 3, 4. Now we don't end up at our start location. The Burgers vector goes from the start to finish. That's what the SF stands for. And we end up with this Burgers vector. Notice that this Burgers vector can be parallel or anti-parallel with the line of dislocation. So in that case, where the Burgers vector is parallel or anti-parallel with the line of dislocation, now we know this is what's called a screw dislocation. So these line defects can be seen in transmission electron microscopes as dark lines. It's also possible to have a mixed dislocation that starts off in one part of the crystal as a screw dislocation and then ends up in another part as an edge dislocation. So why are we spending so much time thinking about these? They're very important in terms of understanding how the material gets deformed. If we think of a crystal lattice like this, if it was perfect and we wanted to deform it, we would have to slide all of these atoms with respect to all of the atoms on the bottom. That would take a huge amount of force, and the theoretical strength of materials is many orders of magnitude larger than what we're actually observing. So what's actually happening inside these crystals? What's actually happening is that instead of having to have all these atoms in unison slide over, we just need to have this dislocation move one step at a time until it reaches the other edge. And now what have we done? We've permanently deformed our crystal. We've formed a step on one side. And this requires a lot less stress. And this is the mechanism which gives us ductility in these crystals. If we want to strengthen the materials, then we can interfere with the movement of these dislocations. So dislocations are very important for understanding the theories of malleability and strengthening in metals and materials in general. So we talked about this. Actually, let me come back to this slide over here, and we're talking about the movement of dislocations, and I will just play a little video. This animation nicely shows dislocation, glide, and climb. So this is dislocation, climb, and then another mechanism of dislocation movement is climb. Another video of dislocation glide can be found at the University of Cambridge Do-It-POM site. So on this site we see dislocation glide being illustrated. So we have an edge dislocation right here. We're applying a stress to the crystal and we're seeing it move. Sorry, let me just start at the beginning. We have a edge dislocation right here, and we're seeing it move. We see that the atoms move parallel to the Burgers vector, and the dislocation line moves perpendicular to the line. The dislocation line in this case is coming out of the page. These arrows here, this arrow here, is the direction of the shear stress being applied. Now, what would happen if we did not have a dislocation? How would the crystal deform? And that's shown in this video here over here. If that were the case, then all of the bonds would have to be stretched simultaneously, and that would take a lot of stress. So we've seen that crystals deform as planes of atoms move with respect to each other. We can be more specific about this and talk about what are called slip systems. A slip system is a combination of a slip plane. For example, here the 110 type plane is shown. On the 110 type plane, we can slide these two halves, as it were. There's about four directions, well, at least four I can see, but just two being illustrated here. And these two directions are the 111. We could of course be sliding along this direction as well. Okay, the 110. That would be a different slip system. The slip system being shown here is a combination of the plane and the direction. Here we see slip planes and directions in metallic structures. In BCC metals, we've got a set of slip planes here, and these are the slip direction. FCC, HCP, there's a note here. It says some of these are only available at elevated temperatures, and we see here for inorganic compounds here being shown here, and also for the silicon covalent structure. Now, I've been mentioning stress and strain. We did discuss it a little bit in the first chapter when we look at material properties. But what is stress and strain? So stress is simply the application of a force to a material, and what we do, we normalize that force by the cross-sectional area over which that force acts. In the case of a normal force, the force being applied is normal to the cut surface. So imagine, let me see if the bottom slide, nope, it doesn't. So if we were to take a sample like so, if we were to cut it here, I've just drawn it enlarged. So this cut surface here, the normal to that would be this direction. If we apply a force in that normal direction, that's called that would be a normal stress if we divided the force by the cross-sectional area. So sigma is the letter given to normal stress. And that is going to equal the force normal to the cut area divided by the area. Alternate to that is shear stress. With shear stress, let me use a different color, we apply a force that is a direction within the plane. So that's F shear, and I will distinguish that from F normal. Shear stress is given the symbol tau, and that's going to equal the shear force divided by that same area. Shear stresses are really important for understanding the deformation of materials, because that's what's going to cause sliding of one plane relative to another. If we were to apply a shear stress to the sample here, what will happen, it will start to become inclined and take on the shape shown by the dotted outline right here, and this face here will start to incline by this angle phi. That change in shape, so change in shape is related to strain, and in this case the strain is given by this angle in radians. The shear stress in this case, as before, tau, is going to equal the shear force being applied. Notice that these are equal and opposite, and that's what allows the material to be kept in equilibrium. But when we do that, we're creating shear stresses in the material. That's going to be F over this area A. This is the Piles-Navarro shear stress. It's the shear stress required to move the distortion from one equilibrium position to another. This is the shear stress. It's equal to C, which is a constant for the material, times E, the natural logarithm, or the base for the natural logarithm, raised to the power minus K, again another material constant. D is the interplanar spacing. So the larger the interplanar spacing is, the less stress is required to slide those planes over one another. B is the magnitude, the size of the Burgers vector. So the larger the Burgers vector is, the larger the distance we have to move the dislocation to its next equilibrium position, and so that requires more stress. So if the Burgers vector is small, then what we predict is that the shear stress along that direction will be reduced. So we talked about that, and so because of this we predict that slip systems with a smaller value of B will require a lower shear stress for deformation, and we can use techniques of actually increasing B to harden the material. We talked about the shear stress. A particular type of shear stress is called the critical resolve shear stress. The critical resolve shear stress is the shear stress required on a particular crystal plane required to cause slip in that particular direction. So you see below the critical resolve, before that critical value, you don't actually produce a permanent deformation. The deformation is elastic, but then once you exceed that, we get movement of the dislocation and we get permanent deformation. So when we stretch a material, we're actually causing shear forces within the material that causes slipping. So if we're just applying a normal force as shown here, and the stress being the normal stress being F over A naught, that actually results in shear forces. Let's see how. Let's consider a plane within that sample which is inclined with respect to A naught. If we do such a cut, this area A is given by this relationship here. We see the area A is larger than A naught, and A cosine phi, the angle between the normal to this inclined plane and the original area here, is given by the green vector. In such a case, A naught is equal to A cosine phi. We can see that from trigonometry. Therefore, this area A is equal to A naught over cosine phi. So just to define further, phi is the angle between the force we're going to apply and the perpendicular to a particular plane. Okay, that's going to be our slip plane. So we've talked about the force that we've applied F. Now let's resolve that force F in parallel to the direction of the slip direction. If gamma is the angle between F and the slip direction, then the resolve value of this force parallel to that slip direction is going to equal F cosine lambda. Putting all this together, we have that we know the critical resolve shear stress will be the force parallel to that slip direction divided by the area. We know that the area is going to equal A naught divided by cosine theta. F over A naught is equal to the applied normal stress to the sample. So now if we know that the material starts to yield at a certain stress, then we can find the critical resolved shear stress by multiplying that by the product of cosine lambda and cosine phi. So here we see a diagram from the textbook which reiterates what we just learned. So for example, here we have a slip direction on a slip plane. Here the force has been resolved along that direction. And we see here how slip has occurred on a certain dislocation. We see the angle phi here being the angle between the normal to the slip plane and the direction of the applied force, which is perpendicular to the original area. So here we see a table of critical resolved shear stresses for some different materials. So we see here that in FCC, the critical resolved shear stress is quite small. That's probably because the planes are close packed, which result in the smaller Burger's vector. This results in a ductile material with BCC. The critical resolved shear stress is quite large, so this makes a very stiff and brittle material. Same with similar situation. Oh, with HCP, even though the planes are close packed, so we get a low critical resolved shear stress, but there's a limited number of slip systems, which results in a relatively brittle material. Okay, let's apply this to this problem here. We have a single crystal of metal that has the BCC structure, is oriented such that the tensile stress applied in the 010 direction. If the magnitude of the stress is 2.75 megapascals, compute the resolved shear stress in the 1 bar 11 direction on each of the 110 and 101 planes. So I've drawn out the situations in these diagrams. I've drawn the unit cell in blue and indicated the 1 bar 11 direction. So that is going backwards here. So we're going H in the direction H, go -1, +1 in the K, and +1 in the L. The force direction is in the 010, so that's along the K direction. So lambda is this angle, and it's the same for both. The angle between the normal to this plane here, the 110, notice that it cuts the H direction at 1. If this is the origin at the back corner there, it cuts the K direction at 1, and it doesn't cut the L direction. This is the 101 plane. This is the origin. It cuts H at 1, L at 1, doesn't cut the K direction. Now let's look at the angle between F and the plane, which is colored in green. So we're going to get an angle less than 90 degrees here, but here the angle between F and the normal to this plane is 90 degrees. So let's see what result that gives us. The equation is that the resolved shear stress is going to equal the applied stress times cosine lambda times cosine phi. Now, cosine lambda is the same in both, and let's see how we can calculate that. So we've got the direction of the force here, and we can just call this direction A. Now, next thing we need, of course, is we've got the direction, the slip direction. So we can call this F sub D, S sub D is 1 bar 1, 1. Okay, now how do we find the angles between this? We can very easily use the property of dot products. So with dot products, we know that if we have two vectors and we take the dot product of them, in this case that's going to equal 0 times 1 bar, which is 0. 1 times 1 is 1, plus 0 times 1, this equals 1. Okay, now we know that this is equal to the size of A times the size of S sub D times the cosine of the angle between them. So therefore, we can see that cosine lambda is 1 divided by the size of A. The size of A is just 1. The size of S sub D is root 3. So now we see that cosine lambda is 1 over root 3. And if we like, we could even find out what lambda is. Our cosine D of 1 over root 3 it's just A cosine D, sorry. That is 54.7 degrees. Okay, very good. Now we've got that, but cosine phi is going to be different in both cases. Now, to find phi in both cases, let's make use of the fact that for a cubic cell, the direction 110 is perpendicular to this plane. So we can say that here 110, the direction 110, dot that with the f direction. This is equal to the size of this vector, which is root 2. Again, I'm just using dot products, times 1 times the cosine of phi 1. Okay? So this gives us the angle between the normal to this force here and direction of f. So therefore, we can see that cosine phi 1 is 1 over root 2. Now let's look at the second case here. 101 dot that with 010, that is equal to 0. And this is equal to the size of the first vector, root 2, times the size of the second one, 1, times the cosine of phi 2. So we can see that phi 2, or rather cosine phi 2, is equal to 0. So therefore, as we guessed, phi 2 is 90 degrees. In this case, phi 1 can be solved for or calculated. That equals 45 degrees. Okay, now we have this information. We can calculate the resolved shear force in each of those slip directions. So for the first system, which was the 110 1 bar 11, And let's remind ourselves what sigma was. Sigma was 2.75 megapascals. The resolved shear stress of the applied stress was 2.75. Okay, that's the sigma in this equation. Then the cosine of lambda is 1/3, or 1 over root 3, sorry. And the cosine of phi is 1 over root 2. So this is 2.75 over the square root of 6 megapascals. Which is 1.13. Now let's look at the other system, 101 and the 1 bar 11. The resolved shear stress is 2.75 times cosine lambda, which is 1 over 3. I mean 1 over root 3, sorry, times the cosine of phi, which is 0. So this equals 0. So this means that we won't experience a slip in this direction, with this system, because the resolved shear stress on the applied force is 0 for that system. But we may experience slip if it's sufficient enough. Okay, this is there's no information given here saying that this is higher than the critical shear stress required to cause slip. But this is how we can resolve a shear stress for a slip system. Okay, let's get on to our last, which is a type of defect, which is the plane and surface defect. These are two-dimensional defects. The material surface is a defect. So with the material surface, notice that we have a reduction in coordination number for the atoms. And so they're going to have higher energy at the surface as a result. Then we have grain boundaries. Let's have a look at what grain boundary is. If we have a look at this solid sphere representation, 2D representation, we can see we have three regions here of regular stacking, A, B, and C. While the stacking is perfect within each of these regions, where they meet, we see there's a mismatch in the plane directions. So here, actually shown above here, we have an angle of misalignment between the two sections. So we can have what's called a high angle grain boundary or a low angle grain boundary shown here. So these grain boundaries can be easily seen in micrographs. Let me show you this micrograph here. We can, when we look at the cross section of a sample under a microscope, if we treat that sample with some chemical that will etch away at the grain boundaries, we can see them quite clearly. And here we can see that this sample is composed of single crystal grains with a boundary. That's what we mean by that. So the grain boundaries can impede dislocation movement and hence strengthen the material. And there's something called a Hall-Petch equation here, which gives us a relationship between the yield stress and the average diameter of the grains. So K is a constant. The smaller d is, the larger this parameter becomes. So the smaller diameter of the grains, meaning there's more grain boundaries, results in strengthening. So this is the Hall-Petch equation. So let's talk about how we actually measure the grain size. And there's different standards that have been created, and these standards are maintained by the American Society of Testing and Materials. I encourage you to join the ASTM Society as a student member. This is free for students, and I'm actually giving you extra credit for doing so, and you'll see the assignment posted on Canvas. So the ASTM method of grain size determination, I've made a mistake here. The grain size number here should be G. Okay. The ASTM grain size number G is given by the following relationship, where N sub E is the number of grains per square inch at a magnification of times 100. So this is based upon English units. So this thing here, so I don't know if I went over the equation. So we've got G, and that equals 1 plus the logarithm base 2 of N sub E. Now it's more typical to have markers on our micrographs that are in micrometers or millimeters. So in this link here, you can link to the original standard definition or description, and you can see that it's also given where Na is the number of grains per square millimeter at a magnification of times 1. So you can easily derive this equation from the preceding definition of G. So let's see how to apply this. Let's have a look at this micrograph. What's the grain size number for this material? Well, we have a scale marker on the micrograph that tells us that this dimension here is 325 micrometers. Let's take a sample here. If we were doing this properly, we would take many samples. But let's just look at sample 1. So this is a sample of an area in the micrograph. In this sample, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. We could count 2 halves as a 15, so 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, and I'll call this 33, 34, and 35. Yes, perhaps I could take all these little pieces here and call it 36. So how can we write N sub A, which is the number of grains per millimeter? So I just counted 36. This is 325 micrometers. There's 1,000 micrometers in a millimeter. So this area is 3.25 or 0.325 millimeters squared. So let's calculate that out. 36 divided by 0.325 squared. I get 341. Okay, so the number of grains per square millimeter and magnification of times 1 is 341. Great. Let's convert this to grain size number. So this is going to be minus 2.95. I'm just rounding the precision. Plus 3.32. Log base 10 Na. Let's calculate this out. So we've got minus 2.95 plus 3.32 times log 10, 341. And this gives 5.5. So for this region, we have a grain size number of 5.5. Of course, we should take more samples and get an average value of Na. That's recommended by the standard. So these mechanisms, where we've understood the concept of dislocations and how they move and how that determines the strength of the material, by understanding this mechanism, we can understand mechanisms by which you can actually strengthen the material, okay, such as strain hardening, solid solution strengthening, and the final one is grain size strengthening, which and we'll study these as we come up in the latter chapters. Thank you.